This is a quick run through of some slides I have on hydrogen bonding specifically in water and its effect on how things are soluble in water. You don't need to watch this video in order to do the intermolecular forces homework, but I had it on the lesson plan for today, so I'm just going to make a quick run through these slides. So this is hydrogen bonding and intermolecular forces, particularly as it relates to water. So, if I can get it to start. There we go. So, water molecule is bent in shape. The OH bond is extremely polar. Because the molecule is bent, the dipoles do not cancel, and therefore a water molecule has a positively charged end and a negatively charged end. When it comes to intermolecular forces, water does exhibit dispersion forces, but they're not the main driver in water. Because it's a polar molecule, it also exhibits dipole-dipole interactions. That is more significant. But the most significant intermolecular force in water is hydrogen bonding. Because of the strong hydrogen bonding in water, water can actually form a skin at the surface. So water really has no affinity for the gas molecules in air at all. And so at the surface of water, the water molecules all crowd together and try and hydrogen bond to each other. And so you wind up getting this skin called surface tension. You may have observed on the water, if you do things on a river or, in some nature video, watching little bugs running across the surface of water because of the little skin that's formed by surface tension. I'm not going to play this video, but if you want to look at these slides in Veracross, there's a link here to the scene in The Incredibles where Dash runs across the water. Now we're going to talk a little bit about solubility, and the fundamental principle of solubility is what I've got outlined down here in red at the bottom, which is that like dissolves like. So polar solvents tend to dissolve polar molecules. Non-polar solvents tend to dissolve non-polar molecules. And we know from just popular culture that oil and water don't mix. And the reason that is true, that you can't dissolve oils in water, is because their intermolecular forces are so different. Water is primarily engaged in hydrogen bonding. Oils are large non-polar molecules that have vast dispersion forces, and so they really have nothing in common with water when it comes to intermolecular forces. And so you can't dissolve an oil in water on its own. So nonpolar solvents dissolve nonpolar molecules. Nonpolar and polar molecules tend to not mix well, and we call this phenomenon like dissolves like. Water, so what will water dissolve? Water dissolves ionic compounds well, and I'm going to show you a slide in just a second that shows you why it does that. So things like sodium chloride and other common ionic compounds do readily dissolve in water, and the reason that they do is because they have positive and negative charges, and water has strong partial positive and negative charges in its structure. And so that makes for good solubility. And then just other polar things, alcohols, acetone, other small polar molecules will dissolve in water pretty well. It is also possible, and the purpose of this slide is just to say, it's also possible to dissolve nonpolar substances in water if you have what's called a surfactant. And a soap is a type of surfactant. And so schematically, I've just kind of got a picture of a soap molecule here. It has a polar head group, and that's what's on the left and called hydrophilic. Hydrophilic means loves water. And it has a non-polar tail. That's what's shown on the right-hand part, and it says hydrophobic. Hydrophobic means water-fearing. And so if you put soap into water, the reason that it can dissolve away grease when you're cleaning things is that the hydrophobic ends, the long tail parts of a bunch of soap molecules will get together and dissolve a piece of grease, and then the head ends that are soluble in water will carry the whole thing away in aqueous solution, and that's how you're able to clean the grease off of your dishes. This is how, two things on this slide. This is showing how it is that water can dissolve ionic compounds, and we're just using sodium chloride as an example here. Sodium is positively charged, and so when you put it into water, the water molecules all orient themselves around a sodium ion so that their negative oxygen ends are pointing toward the sodium. That similarly is the way I was describing how surfactants dissolve greasy things. This is how water molecules dissolve ions. They orient their negative side toward the positively charged sodium ion, and then the rest of the molecule just helps, then just goes off, and this kind of little cage dissolves in the rest of the water. The chloride ion, which is partially negative, the water orients itself so that all the partially positive ends of the water molecule are oriented toward the chloride, and that forms a little cage, and then that whole thing just goes off and gets dissolved in water. This is a specific picture of a soap molecule. This is called sodium stearate. You don't need to know that. This is the hydrophilic, water-loving end. And this is the part that makes soaps soluble in water. This is the hydrophobic tail. This is the part of a soap molecule that allows soap molecules to dissolve oily things. I don't think there's anything of any great significance to this slide, so I'm just going to finish it up. Thanks for watching.